A physics professor reduces his moment of inertia by 25% while spinning on a rotating stand, and thus speeds up his rate of spin. By what percentage did he increase his rotational kinetic energy? So this problem is based on a demonstration that I do where I usually hold masses in my hands and I have somebody start me spinning at a moderate speed on a rotating stand, and then I pull those masses inward and I actually wind up getting up to a pretty high, maybe dramatically high rate of spin. The way I'm going to analyze this is through conservation of angular momentum, because really this demonstration is a dramatic demonstration of what is implied by the conservation of angular momentum. So in other words, I'm going to say L initial is equal to L final. In contrast, though, to the example we just did where there was a rocket car with a tether, I'm not a point mass. So the person doing this is not a point mass. So we're going to want to use the I omega formula for angular momentum, and since the moment of inertia is being adjusted, I'm going to subscript that with an initial, and then for the final angular momentum, I'm going to say it's I final, in other words, final moment of inertia times final angular velocity. And so the reduction of that moment of inertia implies an increase in rotational velocity, thus explaining why the physics professor speeds up his rate of spin. This question is a little tricky to get to, and it involves some different ratios. So what I'd like to do here is maybe do some cross multiplication, and I can divide both sides by omega final. Oops, let me make that a slightly better looking omega final there. And I can divide both sides by I initial to get this equation. The information that I'm given about the 25% reduction of moment of inertia could be interpreted that the final moment of inertia is at 75% of what it originally was. So that means this ratio of I final to I initial should be equal to the number 0.75. This information I think is going to be useful for calculating the ratio of final kinetic energy to initial kinetic energy. So that's the thing I'd like to set up next, because I think when I get that as a number, I'll be able to figure out what percentage increase that reflects. So the formula I'll use for that is the rotational kinetic energy formula, 1/2 I omega squared, and this should be final subscripts on this one, divided by 1/2 I initial, omega squared initial. And then I can simplify that. I can cancel off those 1/2s and get a few simple ratio here, like I final over I initial multiplied by omega final over omega initial, but that whole thing is going to have to be squared since these two both had squareds, but I'm going to just look at that as the whole ratio squared. I have I final over I initial, right? That's equal to 0.75, but omega initial over omega final equals 0.75 implies that omega final over omega initial is equal to 1 over 0.75, since this is the reciprocal of this ratio, and the reciprocal of a number is 1 over that number. So that means, well, let's see, 1 over 0.75, I was going to just put that in here, but then I realized maybe I could recognize or go into a calculator and see that this is 1.33. Actually, in this case, the numbers are simple enough, right? Because this is like 1 over 3/4, which is really 4/3, which is like 1 1/3. So this is really 1.333 repeating, but that's the number that I will put in here. And maybe what I'll do in my calculator though is I'll put this with this, the full repetition of the 3's. In other words, not round it off too much. I could also maybe look at this and just say, hey, this is 3/4 times 4/3 squared. There's a 3/4 would cancel one of the 4/3, leaving a 4/3, which would be equal to 1.33, really repeating. But this suggests that the percentage increase in the kinetic energy should be 33 So at this level of rounding, which seems appropriate given the way the information was presented, the answer I've arrived at is 33% increase, and it looks like that checks out.